Okay, there we go. Okay. Okay. We're going to start a unit now on the electronic structure of atoms. Let's review for a moment the picture of the atom that we have at this stage. The atom now is not the plum pudding model. The atom now has a nucleus. And inside the nucleus, it's got a number of protons and a number of neutrons. Each element has the same number of protons for all of the forms of it called isotopes that differ by the number of neutrons they have. So our nuclear structure is protons plus neutrons are in the nucleus. And we will look later on about that. In Gen Chem 2, we'll talk about radioactivity a little bit more and go into the details of what's actually going on inside the nucleus of an atom. But that's not terribly important if you think about it for chemistry, because Dalton said all of the atoms of one element are exactly identical. Now we know that they're not, but he was basing his argument on chemistry. And what he said was true. Every isotope of an element will react chemically like each other. All of them behave the same. But if you change from one kind of atom to another kind of atom, then they react differently. But now imagine for me for a moment that you've got a sphere that represents one of the atoms in your left hand and a sphere that represents another atom in your right hand, and you want them to react. Well, how can they react? They have to come together and touch each other. Now, what touches when two atoms touch each other? It's that outside, not the nucleus. The nucleus is buried in the middle. It takes 100,000 of them to reach across the volume of an atom. So what touches is what's outside. That's electrons. The electrons that are on the outside and their arrangement is what makes copper different from cobalt and what makes hydrogen different from oxygen. It's the arrangement of the electrons. So right now, our focus is, if we're going to understand the chemistry, we have to understand the arrangement of the electrons. Hydrogen is extremely reactive. Helium doesn't react with anything. It's the major component in the sun, heated to 6,000 degrees Kelvin, and it still doesn't react with anything. There's no chemistry for helium. It doesn't react. So that tells me, and the same is generally true for all of the noble gas elements, helium, neon, and argon especially, and krypton, I guess. Xenon has formed compounds, but they're very, very stable elements, which means the electrons are arranged the way atoms would like to have them arranged, because they don't want to give up electrons, they don't want to gain electrons, and they don't want to share electrons. So the noble gases want to hang to themselves. It's the arrangement of the electrons that makes that true. But lithium, sodium, rubidium, cesium, all of those elements in group 1A will react extremely vigorously with almost anything. And so what makes them very reactive as metals, and what makes them metals, I guess, as well, is the arrangement of the electrons. So that's what we're focusing on in this unit, is what is it about the atom that gives it its unique characteristics as understood by the way the electrons are arranged. So to do that, we have to deviate a little bit, because of the probe we're going to use to understand where electrons are located is light. Now, light is an electromagnetic wave. in matter, it can travel in a vacuum. Now, most other things that you're familiar with, our sound waves that you're listening to me right now, those waves are pressure variations in the air. If you take away the air, you take away the sound. Sound won't transmit through a vacuum. Um, but light does. Light can go through a vacuum. Light does not need a medium. Um, for a long time, they talked about the ether being the medium that light travels through, but we've long since rejected that idea that there is no ether that permeates everything. Light just have that unique ability to be able to travel through space without interacting with matter and can go through a complete vacuum. And it does so and has a velocity equal to c, the speed of light that we talked about. It's 3 times 10 to the 8th meters per second is the speed that light waves travel. And I've told you some things real early about the nature of light and matter and energy and space and time and all of that being particulate. Well, light carries an energy with it. It's called electromagnetic wave because it causes an electric field to vibrate, let's say up and down. And at the same time, it gives an oscillating magnetic field at right angle to that. So a light wave is made of two kinds of fields. It's an electric field and a magnetic field at right angles to each other. And that's why it's called an electromagnetic wave. The interaction that we're concerned with is the electric field because electrons are negative. They're going to be pulled in one direction if the electric field is in one orientation, but if the electric field is flipped to the other orientation, the electron will experience a push. So the interaction between light, electrons and atoms is through light. The speed of light is 3 times 10 to the 8th meters per second. I told you earlier that light photons, light particles, have different amounts of energy and they have different wavelengths. The speed of light is independent of the wavelength. Everything from radio waves and to X-rays and ultraviolet light and cosmic rays and gamma rays, all of these things travel at 3 times 10 to the 8th meters per second in a vacuum. So that's a characteristic of all forms of light, is this constant speed. And I think I mentioned to you that that becomes the ultimate speed. Absolutely nothing can travel faster than that. Now, the relationship between the wavelength and the frequency is the speed. The frequency is how many cycles of light passes you per second, and lambda is the wavelength. So if you multiply those out, you get the speed of light. So the right-hand side of this is that c is always this number, 3 times 10 to the 8th meters per second. So if I know the wavelength, I can calculate the frequency, or if I know the frequency, I can calculate the wavelength. Here's the checkpoint on that. So green light is 650 nanometers, and what would be the frequency of the green light? Well, the wavelength, lambda, times the frequency has to equal this number, 3 times 10 to the 8th. I know what the wavelength is, so I can calculate the frequency. And if you do the math, you get 4.62 times 10 to the 14th cycles per second. So that's a number that's hard to imagine, really. 10 to the 14th vibrations of that electric field in 1 second. So the bottom line takeaway is an electron would experience a push and a pull by this light 4.62 times 10 to the 14th times a second. So when that light comes through matter, the electrons are set into extremely fast vibrations at 650 nanometers. Now, different wavelengths certainly would have different frequencies. And so here's a problem. I often listen to 99.7 on the radio. It's at frequency is 99.7 megacycles per second. What's the wavelength? So you can calculate that. And I hope you will, or whatever is on D2L. This will see if you understand this concept. And remember, to do a conversion in the metric system, you can get rid of that mega just by changing it to what it's equal to. Mega is 10 to the 6. So this is 99.7 times 10 to the 6 cycles per second. And then it would follow this, exactly that pattern up above. Okay. Now you might be interested to, when you calculate that wavelength, it's going to come out in meters. But if you converted that to feet, you ought to do that and see how that compares with the length of your car. I'm not going to tell you the answer. Okay, now, this is what I was talking about with this cartoon shows that different colors of light have different wavelengths. The wavelength of blue light is shorter than the wavelength of red light. Now, I'm showing the wavelength being from the 0 to the next time it comes to 0, but it would work the same way if I took any corresponding points. The peak of this wave to the peak of the next wave would be the wavelength as well. So it's the distance that you could use to reproduce that whole wave. You just slide this one, this end over to this end, and that gives you the next cycle and so forth. So all I have to do is look at one cycle, and then I know what the whole beam of light would look like. And it's producing a wave that looks like that. So wavelength of red light on the red end of the spectrum is about somewhere close to 800 nanometers, and blue light is something close to 400 nanometers. I just use those numbers. They're not exactly correct, but I want you to see a scale that from one end of the visible spectrum to the other end, the wavelength about doubles, going from the blue to the red. Now, the energy of a photon is determined by its frequency, and it's directly proportional to the frequency. If you double the frequency, you're going to double the amount of energy that the wave has in it. Well, you can see that the wavelength of blue light is shorter, meaning the frequency of the blue light is greater than the red light. So blue light carries more energy than red light does, and it's directly proportional to the frequency. So the energy is equal to some constant. This is called Planck's constant, and this is the frequency in cycles per second for one photon. Planck's constant has a value. I'll give it to you when we need it. It's 6.626 times 10 to the negative 34 joule seconds. And I'll give you that number. You don't have to memorize it. We'll use it often enough, eventually you will get it. Now, the electromagnetic spectrum covers an entire, it's a continuum from extremely short wavelengths on the left over here to extremely long wavelengths over here. And the part we call the visible spectrum is this little piece right in the middle. Now, I've got it way out of scale. If I put this on correct scaling, then this visible spectrum would be a line that would be blue on the left and right and red on the right side. It'd just be a little thin line. But this is where the spectrum is, and I've tried to put colors in that indicate as you go across this rainbow of colors from red to orange, yellow, green, blue, violet, indigo, or indigo and violet, I guess is the way it goes. But anyhow, this is the visible spectrum. To the long wavelength of that is the infrared. To the short wavelength side of that is the ultraviolet. Now, you should certainly do know about ultraviolet light, I'm pretty sure. And we've talked about X-rays already and gamma rays already. cosmic rays are just the extension of that. These are very high energy radiation that comes from actually into the sun. The core part of the sun is sending out cosmic rays. And they're so energetic that we don't even talk about them in wavelength. Generally, we talk about them in terms of energy, in millions of electron volts of energy. The infrared region, you already know about a little bit, I'm sure. Maybe you don't know what it is. Now, the visible region is, quote, visible because the receptors in our eye is able to detect radiation in that wavelength or frequency range. We can see those different colors. Actually, we don't see them all. We only see 3 of them. But our brain is able to interpret the signals that come from those 3 sensors. Instead of just being the primary colors, we can see millions of different shades of color. But we're actually only seeing 3 of them, and your brain is interpreting the signal from those 3 nerve endings as a particular color. Now, we do see infrared, but not with your eyes. You see infrared with your skin. It's heat radiation. And we can sense where a heat source is. I mean, if you're standing close to a fire, campfire some night, you know that the side of you that's warm, you can tell that the fire is over there somewhere. Even if you couldn't see it, you could tell that where the fire was. You could sense the heat with your hand. And we make use of that as a military application in, well, the oldest version of these was called a Sidewinder missile. And what they do is they have an infrared sensor in the nose cone. So say you want to shoot down a plane, if you take one of these kinds of missiles and fire it toward the plane, all you have to do, well, in fact, most jet planes emit what's called a contrail. If you've ever noticed, when a jet goes over, you see a white cloud behind it that kind of disappears over time. That's steam, and it's making little water droplets that you're able to see. So sometimes you can see the contrail and you can't even distinguish the plane that's causing it. Well, with a Sidewinder missile, you don't have to worry about that. All you got to do is aim it toward the contrail. When the missile gets up, its automatic system takes over, and it starts flying the nose cone toward any source of heat. Just like I said, you feel the right side of your face warmed by the fire. You can take your right hand and point toward the fire. Well, that's what happens with that missile. It's extremely sensitive to heat, so it can detect heat sources. So if you fly it through the contrail, it'll turn on a dime and head right up that contrail and fly right up the exhaust of that jet plane and take it out. So it's a very good military missile, and we've got much better than the old Sidewinders, but they are extremely fast and extremely responsive, which means essentially that if you get a lock on from one of these kinds of missiles, you can't outmaneuver it. You can turn as fast as you want to or do whatever you want to do, and you can't avoid getting knocked out. But we know another way to do it. There's a couple of ways that would work, but what they generally do, if you're not equipped with your own flares or missiles, our planes do have them. So if they get a lock on, knowing that missile now, the Sidewinder part, the infrared part, has aimed it, and now it's on radar lock on, and it's followed then from then on with radar. And so if you detect a radar lock on, you can cut your engines immediately, fire off a flare in the direction you were going, and take a quick nosedive. Now, when the heat source cools on your engine, the flare you shot out has more heat, so the missile will follow the flare, and you can fool it that way. Um, I, it's not top secret, but we have also very fast electronics, and we can detect a radar lock-on. And the way the radar is going to work with a missile is it's going to take the reflected beam off that it gets when it hits your plane and determine how far you are and what direction you're going. Well, we've got electronics so fast now that we can intercept and pick up a radar signal coming in. We can phase shift it and send it back and make it appear like your plane is 200 yards to the right of where it really is. And the missile will follow the lock-on, follow its signal, but the signal you're sending back is more intense than the reflected signal. So we've got military ways of doing this. A lot of it based on microwave technology, on infrared technology. Microwaves you know about already because they are the way we cook things. The microwave, what it does is it causes the molecules to tumble. And as they tumble and bump into each other, as I mentioned way back early, temperature is this random motion of molecules. And so when they bump into each other and bounce around off each other, that makes their motion much more random and creates heat, makes it hot. So the microwaves actually are tuned to water or to metals. Metals will be affected by microwaves as well. I'll mention that in a minute. But anyhow, the microwave is tuned to water. So if you've got popcorn, it's got moisture inside the popcorn sealed with a little heavy husk on the outside. When you heat that up, it builds so much pressure and steam inside the kernel that when it pops, it foams up and fluffs up the popcorn and makes a nice treat when you're watching a movie. Well, you can pop your corn, of course, in a paper bag if you want to. If you buy Orville Redenbacher, it's got not only that, but on the bottom of it, it's got a piece. It's got a piece inside that's got metallic particles in it, and the metals reflect the microwaves and makes it get even hotter. You know, probably if you put a loaf of bread in an oven with a twist tie on it, you see some fireworks sometimes. Well, the reason for that is that the microwaves, when they hit the wire, they're traveling back and forth, and they cause the electrons to flow back and forth in the wire, so that at one moment, almost all the electrons in the wire are over on one end, and it's very negative, and over on the other end, it's very positive, and it can actually spark from one end of that wire to the other end if you put it inside a microwave. And if you do that very often, it'll destroy your microwave. I'll tell you another story, true story. When I was in graduate school at Vanderbilt, one of the projects I did, I used microwaves to generate extremely hot temperatures to break down big heavy molecules into smaller pieces. And then I would study the smaller pieces of molecules, or I would use the light generated by that process. And we had a unit that they used to use in the hospitals at Vanderbilt to treat arthritis. It was called a diathermy unit. It was just a microwave transmitter that was able to beam microwaves into arthritic joints. And that would would relieve some of the pain and suffering of arthritis. So we had those that we were using in the lab, and we were using them to generate high power. So my roommate and I worked in the same lab. We were wondering one day, would it be possible to cook with this stuff? Because you can heat things extremely fast. Well, the way we were doing the experiment to get the very high temperatures was we would take the microwave antenna and wrap aluminum foil around it, and then put our sample inside the aluminum foil. The microwaves then got reflected off the aluminum foil, and would actually melt glass down in the middle of the microwave beam. And we kept blowing out the diathermy units, because whenever those microwaves came in and bounced around inside, a lot of them bounced right back up the antenna wire and burned out the magnetron tube. So we got a cavity that was built so that the reflected wave was always out of phase with the transmitted one. So the reflected wave traveling along the transmitted one canceled each other out, or canceled out the reflection wave anyhow. It was smaller. So it canceled it completely out, and it was able to, I could use that cavity. And so that's what we decided to try. Can I build a cavity big enough to hold a turkey? And I did the calculations and rapidly came to the conclusion that for a cavity the size of a turkey, there would be no way to cancel out all the reflections, and it would just burn out the tube. So people wouldn't pay the expense of getting a microwave oven if it's going to burn out the first time you try to cook a turkey in it. So we concluded that you couldn't use microwaves to cook. We were too smart. You know that fan that you hear when you turn the microwave on? It is a fan, but that's not the main purpose of it. If you imagine the microwaves going left to right from the transmitter, the fan blade comes over, the microwaves hit the fan blade and are reflected down into the oven. They bounce around and heat the stuff in the oven. The reflected wave comes back out, but by that time the fan blade's moved off, and the reflected wave goes straight up and is caught in an absorber. If I'd thought of a $30 fan, I would have invented a microwave oven. You can sometimes be too smart for your own good. That was a case where we came to a very wrong conclusion. You can, in fact, cook with microwaves if you protect the transmitter. Okay, well, enough of that. Radio waves, that's a continuum. I guess the only really exciting thing for me is out at the end of this. If you take a radio transmitter and aim it toward some galaxy out in space, you will pick up radio noise that can be imaged. And you can determine then the size of that galaxy and all kinds of things about it, looking at the radio waves instead of looking at visible light, like you might get from the Hubble telescope. And these radio waves we can pick up from Earth, and we have several radio transmitters that are able to resolve pretty good sized objects. Now, a radio transmitter is not going to resolve things like an individual star typically. They would typically be able to pick up galaxies and things like that, but not individual stars. But if you aim that radio transmitter in between all of these known galaxies, in regions where at least we don't think there's any matter at all, you still pick up a radio frequency. And It's a constant amount of radio energy that it's not very much. It's the amount of energy that a piece of steel would radiate at 2 degrees above absolute zero. That's the background radiation. But this excited scientists all over the world because this now shows that the entire universe is bathed in energy that came from the Big Bang when everything was created. So this gave scientists near proof that everything was created at one moment in time, at one instant in time, at one point in space. And the energy of that explosion flew out in all directions and now is a part of the space that we see. And that's nobody can come up with any other explanation for that. And so that gave scientists the belief that there was a moment of the creation that they call the Big Bang. But for the rest of us, that gives us also confirmation that the universe did form at one instant at time, at one moment in space. And I happen to believe God did that. But that is physical evidence of a moment of creation. Okay, I wanted to give you some background about all of this good stuff that we're talking about, but I wanted you to see the infrared, the whole region of the spectrum. The spectrum is a continuum, not just the little visible part that we see, but all of the other radiations that we know and experience. Now, I've mentioned way back in lecture 1 that energy is quantized. It does have a smallest particle, and it has a particular amount of energy. So energy flow is not like a stream that's continuous. Instead, it is a stream, but just like a stream of water is really a stream of little tiny droplets, which are a stream of little tiny molecules. The same thing is true for energy. Energy, flowing energy is a flow of these little discrete packets we call quanta. Quantized meaning only certain values are possible. And we saw the energy of the light is Planck's constant times the frequency. If I know the wavelength instead of the frequency, it's hc over lambda. C is the speed of light. Planck's, and that's 3 times 10 to the 8th meters per second. Planck's constant is 6.626 times 10 to the negative 34 joule seconds, and the wavelength has to be in meters. If you put in all of those particular units, the energy you get is joules. So here's a checkpoint on that based on the earlier one. What is the energy of a whole mole of photons radiated by at 99.7 megacycles per second? Okay, and your checkpoint would be either this one or one like that. And we've got to remember, I want to back up again to here. When we talk about the energy, this is the, if I put in Planck's constant, the speed of light, and the wavelength of one photon, I get the energy of one photon. So if I wanted the energy of 10 of them, I'd take that answer and multiply by 10. If I wanted that energy in terms of a mole, I'd take that energy and multiply it by Avogadro's number. Okay. Now, here's the way the photoelectric effect was used by Einstein to understand how electrons are attached to metals and how they can be detached from metals by light. It's called the photoelectric effect. Essentially what you have is a discharge tube, way a lot like what was used by some of those earlier artists. But you put a voltage across them, make this electrode negative, let's say, and make this one positive. And on this one, you have a little target down here at the bottom. If you make that target out of something like cesium is often used. Then when you take visible light and hit that, it will knock an electron out. And the electron then is attracted toward that positive plate and travels across and causes a current to flow in the external circuit. Another quick story. Way back years when I was growing up, the local grocery was called A&P Grocery. It was a big food chain for the time. And out in front, they had two posts, and they had lenses on them. You could see the lens. You didn't have enough light to see the light beam across it, but there was a light beam that went across. And one of them was a transmitter of the light. The other one, the light was collected by that metal, hit that metal, and then caused the current to flow. Well, as long as that current was flowing, it was energizing a magnet, a relay that would cause a current to not flow to the motor that opened the door. But if you broke that beam, then the relay flipped to the other position, it energized the motor and opened the door. So when you walked up to the A&P store, you didn't have to push the door open. It would just open magically for you when you broke that invisible light beam. Well, man, I thought that was so cool. I'm standing out there between those two posts, slipping my hand in and out and watching the door just fly open and goes and open and goes. And I thought that was so funny until the manager came out and chased me away. But now the same thing happens, but it's not amazing to you. You don't use the photoelectric effect anymore. They use a little sound emitter and absorber that you don't even notice. It's up at the top of the door, beaming sound waves out that's in a frequency you don't hear, and they hit you as you walk up. The reflected beam says, hey, there's somebody by the door, and it opens the door. So it works the same way, but this was an application that Einstein did. But he did something a little more. He could measure the kinetic energy, and what he did was he put a little screen in here, and he made that screen negative. Now, that screen was negative. The electrons were negative. So when the electrons started flying across here, when he turned the voltage up on that screen, there would be some voltage that would stop the current from flowing. That was the energy of that electron in electron volts. So he was able to measure that kinetic energy, and he did it as you change the frequency or color of this light. And what you saw is if you plot the energy that you get versus the frequency of the light, you get a straight line, showing the energy is proportional to the frequency. The slope of that line, any straight line has y equals mx plus b. This is the slope, and that's the intercept. The place where the function crosses the y-axis when x is 0. It'll be this value right here. So the slope of that line then is Planck's constant, and that's how it was measured. So let's take a maybe 10-minute break or so, and then we'll pick back up here maybe. And we've already done the lab introduction, so I'll take a few minutes, around 10:30 or so or 11 to see if you have any questions about the lab and or any problems with Excel, and we'll pick back up with that then. But let's take about a 10-minute break and give ourselves a chance to rest. And I want to recording. And let's do the screen share. Okay, now everything gives off radiation. It's a type of radiation that's generally heat. You know, your body temperature is 98.6 if you're healthy, or something close to that. And maybe you don't know it, but you radiate the equivalent, I do too, we radiate the equivalent of about a 100-watt light bulb. And that's why whenever, well, for example, back during the oil embargo many years ago, you probably don't remember it, maybe not, haven't even heard of it, but during the time of the um, invasion of Kuwait by Saddam Hussein, in that time frame, um, the oil coming from the Middle East essentially disappeared. And there were lines all around, um, maybe a mile or so, around service stations of people trying to get gas, usually around a block or so, anyhow, for almost any of them, for almost any time of the day, if they still had gas to sell, or gasoline. And the government decided it would be smart if we set the thermostats down about 4 or 5 degrees, um, so that we weren't using so much energy for heating in the wintertime. This was a winter time situation. And we wouldn't be using so much heat. So they sort of passed a directive, not maybe a law, but all public buildings and all large business buildings had to lower their thermostats 5 degrees. Well, they did that. And one of the things afterwards, they started looking at power consumption. Did it, in fact, do what it was supposed to do and cause us to use less heating oil and so forth? They found out in, especially New York City, the opposite was true. When they lowered the thermostats, they actually used more energy. And finally, they came to realize in those huge office buildings, there may be thousands of people in that building somewhere. And they and all of them were radiating like a 100-watt light bulb. So in the wintertime, when people were at work and everybody was in those buildings, it wasn't the heater that was keeping it warm. It was the people that was keeping it warm. In fact, it would be uncomfortable if they had all those people in that building, and the system, when they set the thermostat, was actually using the air conditioner to cool. And so when they set the thermostat down lower, it had to cool more. So black body radiation is the radiation that everything gives off, and everything does, and it's proportional to the temperature uh, of the object. The hotter the object, the more radiation it's going to emit out through its surface. Now, this was well known. It's a Stefan Boltzmann derivation. It's proportional to the fourth power of the temperature. So the absolute temperature, if you can't double it easily, it's too big a number. But if you did double the temperature, you would raise 2 to the fourth power. You would actually produce 32 times as much heat. So the temperature is, the amount of radiation per unit surface area is determined by the fourth power of the temperature. Now I'm going to use that to do a little derivation for you to predict what the temperature of the Earth should be. And what we're going to look at is, there's the sun, 93 million miles away is the Earth. The sun is emitting radiation in every direction. And just a little segment, just this little fraction here of that whole amount is captured by the Earth. And that's what causes the Earth to have the temperature that it does have. It gets its radiation from the sun and distributes it again around the Earth to regulate its temperature. And So we're going to make use of that. The amount of radiation that the sun, that the Earth receives is its cross-sectional diameter that's perpendicular to the sun direction. And on Earth, the Earth is about, I said 6371.3. That's an average for the radius of the Earth. And it varies a little bit depending on how you measure it and where you get the radius, but it's something, the average value is something like this. I'm carrying extra significant figures, I do know that, but I just wanted to try to give the numbers that correspond to an average value, and I didn't want to restrict it to just say 6,400 kilometers. Now, if you, the area of a circle is pi r squared. So if you multiply by pi and square this number, you get this number, 1.28 times 10 to the 14th square meters. So now that's a lot of area. The Earth is a pretty big thing when you compare it to things around us. But if you compare it to the sun, it's very tiny compared to the size of the sun. But this is the cross-sectional area. Now, the sun has an average temperature of something close to 6,000 degrees. It's 5776 is the best average value. And if we raise that to the fourth power and multiply it by the Stefan Boltzmann constant, this number is the value I told you that is proportional to the fourth power of the temperature. Well, this is the proportionality constant. It's 5.67 times 10 to the 8th. And if you multiply that out, what you're going to get is the number of watts of energy that's coming out per square meter of surface area. So the energy of the sun is 4 pi r squared times the irradiance. And if you look at that and do the calculations that's implied here, you get 3.84 times 10 to the 26 watts. Now, watt is a joule per second. So every second, the sun is emitting 3.84 times 10 to the 26 watts of energy. Now, that's dissipated over this entire surface of a sphere that's a radius of 93 million miles, or 1.5 times 10 to the 11th meters. So you can get the surface area of the sun at the Earth's orbit. And that's where all of this energy is going to come through. It's going to have that much energy, and it's going to pass out through that sphere eventually that intersects the Earth. And the surface area of that sphere at the Earth's orbit is 2.83 times 10 to the 23rd square meters. So if I look at this area compared to this one, that's going to be the fraction of the total energy of the sun that would be captured by the Earth. And if I take the amount, the surface area of the Earth, and divide it by the surface area of that sphere, I come out with a very tiny fraction that the Earth gets. 4.3 times 10 to the negative 10th. Multiply that by 100, that would give you percentage. So you see, it's got to be 4.53 times 10 negative 8% of the sun's energy is actually captured by the Earth. Only this tiny fraction is captured by the Earth. But there's a lot of it. That's how much the sun is actually emitting. We get this fraction, we multiply them together, and this is the amount of watt of energy that the Earth actually captures from the sun, supposing it captured all of it. 1.74 times 10 to the 17th watts. That's a lot of energy. Now, a megawatt is 10 to the 6. And you see, that's what, 3 orders of magnitude above that? So this is thousands of megawatts of energy, and we measure power plants in terms of megawatts. So this is far more energy is coming to the Earth than we would ever use. And so this is why people say that solar energy is enough to power the whole Earth. It is, with lots left over. The problem is just capturing it, and that's something else that we'll discuss at a later time. Now, in order to achieve thermal equilibrium, the Earth has to radiate the amount of energy it gets. If it didn't radiate it, then the Earth, if it radiated less than it received, the Earth would be getting hotter and hotter and hotter. If it radiated more than what it received, it would be getting colder and colder and colder. And so the temperature of the Earth is relatively stable over geological time. Now, there are fluctuations. There's certainly difference between night and day. Temperature 20 degrees difference generally between the daytime high and the nighttime low. And certainly there's seasonal differences. There's a difference in temperature in the winter and difference in temperature of the summer. But winter here is summer there. So it's still okay for the average, you know. So, and people will argue, well, the Earth isn't in thermal equilibrium. Well, it may not be daily. Things can happen on a daily basis, but the Earth is millions of years old. If it just had 1/10 of 1 degree difference per day over the millions of years, the Earth would either be boiling or freezing. So we can argue that, well, maybe you don't think it's in thermal equilibrium, but yes, on a long-term scale, it has to be, or it wouldn't be. It would be either too hot or too cold by now. It's been a long, long time since the Earth and the Sun came into existence. Now, the radiation that the Earth receives has to be radiated back out through the Earth's surface. So the surface area of the Earth is 4 pi r squared. And if you multiply 4 pi times the radius squared, you get 5.10 times 10⁻14 square meters. This is how many watts we get. So the number of watts per square meter is, just divide that out, and you get 341 watts. Now, when I first did this, I was looking to see this particular number because I knew what that number is. If you look up how much, say you want to build a solar collector and you want to generate a kilowatt of power, you look up the irradiance of the Earth, and you can calculate how many square meters you would need at 341 watts per square meter to be a kilowatt. And this number is well known. When I calculated this number from just how I showed you, I was just tickled pink when I looked it up in the handbook and found the same number. It shows that my calculation is accurate to the measured value of watts per square meter at the surface of the Earth. So now I can calculate, well, what would the temperature be if I used the irradiance of the Earth, the Stefan Boltzmann constant, and then calculate the temperature. So if you do that, you come out with 5.3 degrees Celsius. The average value is closer to 15 degrees Celsius. So we're calculating a temperature way too cold. We would not be comfortable if the average temperature of the Earth were 41.6 degrees Fahrenheit. If the average were that amount, it would mean that the northern lakes would freeze over in the winter and never thaw. They wouldn't have time to thaw back out at that temperature. And so we would have very large regions of the Earth freezing solid in the winter. And so this is just certainly not the temperature of the Earth. We know it's not. We know it's somewhere closer to 15 degrees Celsius than it is to 5. Now, let's see how we can make that better. And we can make it better using what's called the greenhouse effect. And I want you to pay attention to the derivation and what I'm doing here, because a lot of people explain this all wrong. So here's the way the greenhouse effect works. We've got the Earth's surface and we've got this energy coming in from the sun. Now, when radiation is absorbed, from any wavelength, when it's absorbed, it is converted to infrared radiation as heat. That little spot gets warmer and radiates that radiation off. So it's radiating some amount of radiation I'm going to call I sub 0. So there's a certain intensity of radiation that's coming out from the Earth's surface based on the energy that's brought in from the sun. So it's emitting this much radiation, and any difference between what came in and what went out would be a warming at that local spot. Now, carbon dioxide turns out to absorb in the same region of the infrared that the Earth is emitting. And so there's carbon dioxide in the atmosphere. Now, for the sake of the argument, I'm just going to put all of the carbon dioxide at one place. And as a spectroscopist, it doesn't matter whether you've got a mole of carbon dioxide in your absorbing beam, and the beam is 3 feet long or 3,000 feet long. Wouldn't matter if you had a mole. It's the concentration of the total number of molecules in that sample that determines how much gets absorbed. So whether the CO2 is just uniformly distributed throughout the Earth, or throughout the atmosphere, or you imagine compressing the CO2 into a layer, it makes it easier for us to model, but it's exactly the same effect. The amount of absorption would be determined by the number of CO2 molecules that are in here, and it wouldn't matter where along that beam of reflected light they were. So I'm going to put them in a layer here because it'll help us to understand the way the greenhouse effect actually works. Now the molecule is going to hit a CO2 molecule. If it does hit it and it's absorbed, now that molecule is in an excited energy state. It's also a gas. So it's tumbling and bouncing around, and it's going to hold that energy in that excited energy state for some brief moments of time, during which the molecule is going to rotate in every possible direction. So that means when the molecules get ready to emit, some of them may be emitting it out, and some of them may be emitting it in, and some of them sideways, and all those directions. But we can imagine that half of the radiation would go out, and half of it would come back due to its interaction with the CO2. So half goes out, half comes back. And so now this same beam of sunlight is producing two regions of absorption, one here and one here. So we'll assume that that's going to average out, and the amount that came in here is going to reflect back out like that. And it's going to interact with the CO2 layer again. Half of that half will go out, and half of that half will come back and create another region of warming. So you see, effectively, this one beam of light is giving more than its equivalent energy that is being absorbed because the CO2 is in there. And then again, this 1/4 I0 goes up to the CO2 layer, one half of that half goes out, and one half comes back. And 1/8 goes each way. So this continues. Okay, let's back it up. So this will just continue, and it keeps on going essentially infinitely. Now what I want you to look at is these values: 1/2, 1/4, 1/8, 1/16 of the original beam is being reabsorbed. Now, if you look at that, the amount that was trapped by the CO2 was the original I0 plus 1/2 plus 1/4 plus 1/8. Now, you factor the I0 out of that, and you get 1/2 plus 1 plus 1/2 plus 1/4 plus 1/8. Now, this part right here is a well-known mathematical series. And if you keep on doing that all the way to infinity, then the sum of those values would be 1. And you can try that on your calculator. Just do that. Do 1/2, 1/4, 1/8, 1/16, 32, 64. Add them all together, you'll see they get closer and closer to 1. If you made it an entirely infinite series, it would be 1. So this totals 1 plus 1. So the total amount of radiation that can be trapped by CO2 is just twice what came in. Now, runaway radiation is not possible because it has a maximum amount. The maximum amount that you can get is just a double what you came in with no carbon dioxide present at all. So that's the maximum amount that could be trapped by the CO2 in the atmosphere. In runaway heating or reaching some, quote, tripping point or tipping point, I think they call it, is absolutely impossible and non-science. It might sound logical, it could, and a lot of people believe in it, but it's absolutely impossible for CO2 to trap more than the initial radiation that it came in. It can it can possibly trap, if there's enough CO2 there, it can possibly trap 1 I0. So you can't get more than that. Now, let's look at this now like particles. A photon is a particle. A carbon dioxide molecule is a particle. Imagine your left hand and your right hand. As long as they don't bump into each other, they are independent of each other. For CO2 to actually absorb a photon, it has to be physically hit by a photon. Now, let's suppose we had an initial I0 of 100 photons, just for the sake of a number. What's going to happen? There's 100 molecules of CO2 up there, and your I0 is 100. Then essentially, if you have no CO2 in the atmosphere at all, then all of that 100 photons gets out, and there's no warming occurring. But you start to put CO2 molecules in there, then something can happen. Suppose you had 10 CO2 molecules in the atmosphere, and you're putting out 100 photons up toward 10 molecules. Well, how many can get absorbed? Well, supposing all 10 of the CO2s trapped a photon, you get 10 absorbed. 90 would escape. Of the 10 that absorbed, half of them would go out and half of them would be returned. So you would get a warming. You'd have 105 photons now in the Earth causing warming compared to the 100 that you had without the CO2. There's an extra 5 that you get because you had some CO2 in the atmosphere. Now, on the next pass, half of that half goes out, and eventually all 5 of the photons that resonated got trapped. Suppose you put 100 photons in, and you've got 100 molecules of CO2 in the atmosphere. How many get absorbed? Well, if it's perfect absorption, all 100 get absorbed. 50 of them are going to go out, and 50 of them would be returned. And eventually, the heating of the Earth would be caused by up to 200 photons worth of energy. You have doubled the amount of energy that got trapped by the CO2. You got another amount of energy trapped by CO2 that is equal to what was already there without the CO2. So you essentially double it to 200 photons. Now, suppose you put 100 photons of energy, and you've got 200 molecules of CO2 up there. How many get absorbed? Only 100. It don't matter how much CO2 you've got up there. Once you get them all absorbed, they're all absorbed. So you would get 100 photons absorbed, just like you did when you had even though you had 200 molecules, the only amount that's going to be affected is the 100 that get absorbed. The others didn't pick up any energy because there was no energy for them to pick up. So the number of photons that you're going to get is going to level off. We spectroscopists know about this effect, and we've worry about it all the time. It's called saturated absorption. So if I get a sample and I try to put it on my spectrograph and measure the intensity of absorption, if I get an absorbance of about 1/10,000th of the amount of energy that's in there, if that's what's left is 1/10,000th, the electronics can't detect it. So your instrument is crazy. It goes wild. It can't, if the numbers it gives you doesn't mean anything. If I get that, what I'm going to do is I'm going to dilute that sample by a known factor, maybe a factor of 10. And then I'll know how the concentration changed by a factor of 10. Now, if I put it in the machine and I read an absorbance, say, of 0.8 or 1 or 1.2, some numbers like that, I know the instrument's working because I've diluted the sample and avoided saturated absorption. We do this all the time. But the people who are just talking about the greenhouse effect and don't really understand it don't know what saturated absorption means. What it means is all of your sample is absorbed. Once you get 100% absorbed, you can't get any more effect no matter what you do to the concentration of the absorbent. So this will saturate it out. Now, when does it saturate out? You can tell that also by, if you know the intensity of the light, you can calculate how many photons are in it. If you know the concentration of the sample, you can know when the concentration of the sample produces a number of molecules of CO2 equal to the intensity of the infrared radiation they're absorbing. That occurs at about 50 parts per million in CO2. Now, that occurred several million years ago, probably very shortly after the atmosphere of the Earth changed from methane and ammonia to the beginnings of the atmosphere we have now, nitrogen and oxygen. And once we got oxygen in the atmosphere, we started producing CO2 because the carbon in the trees and the vegetation, when they react with oxygen, they burn and they produce CO2. The production of the oxygen in the atmosphere led to carbon dioxide in the atmosphere. So several million years ago, CO2 concentration would have reached as much as 50 parts per million. Now, let's see if this, I've got a problem with trying to find that file. Hold on just a second. In fact, I think, well, no, I think I need to do that. All right, let's see if I can locate that file. Whoopsie daisy. And let's don't do that. Let's do this. Let me go over here. I'm going to need to find a file that for you. Okay. Need to go somewhere else. Whoopsie daisy. Okay. And let's do okay, I'm having trouble finding. Okay, if I go back to here and do screen share, it should be, it's not, my file is not showing up. It's on my desktop, but it's not showing up here as one of the ones I can share. Well, no. No. All right. Oh, there it is. Yeah, we got it. Okay. Now, yes, this is a program that does all of the calculations like I showed you a while ago for the greenhouse effect. And it is showing the radiation. Don't worry about these numbers here. The radiation versus the wavelength. And this pink curve that you see is the uh, amount of energy that the Earth radiates. You see it peaks out somewhere in this region around 10 micrometers in wavelength is the region that most of the infrared light that the Earth is emitting is at this wavelength. That's the maximum. But it trails off like this, gets smaller there, and sharply on the short wavelength, high energy side. So this is the kind of radiation that the Earth is emitting. Now, up here, I've got it set so that I can put in different concentrations of carbon dioxide in the atmosphere. And what it will do is uh, it will look at the places where carbon dioxide absorbs. It'll calculate the energy that it absorbs, and then the amount of that energy that would be added back into uh, the amount of energy stored on the Earth's atmosphere, and then recalculate the temperature. So if I put in 0 parts per million, this is the numbers that we saw earlier. My original calculation, it would be somewhere around 5.4 degrees or 41 degrees Celsius. And that would be the temperature of the Earth, average temperature with no carbon dioxide. I want to put in just 1/10 per part per mil of a part per million, 0.1. And what I'd like you to do now is notice we at 41.6 with no carbon dioxide at all. And if we put in 1/10 of 1 part per million, we go from 41.6 to 49.7. Oh, actually, I put in 1 part per million. It's supposed to be 0.1. Yeah. Okay, there we go. So went from a little over 41 to a little over 43, a little less than 44. And what you're seeing right here is the carbon dioxide absorption band. It has a very unique and characteristic shape. It has a little wave on one side, and then it's got a very sharp peak right in the middle and a little wave on the other side. That is a fingerprint that you use to identify CO2 in by analysis using using a spectrophotometer, and we could actually take that and calculate the concentration. Is what we're usually doing. What I've done here is calculate the shape of the band if we put in 1/10 of a part per million of CO2 in the atmosphere. So it does make an effect that you can measure. Now let's change that to 1 part per million. And if I go 1 part per million, that's 10 times as much CO2. The temperature goes from 43.9. Let's see, this is supposed to be a 1 part per million, 43.9 to 49.7. So we started way back at 45, and just with 1 part per million in the atmosphere, we've raised the temperature about a little over 4 degrees. And what's happened is the CO2 has almost completely got to the bottom of the, I've put a black curve in here now to show what you get. The difference between that black line and these pink dotted lines we're seeing here is the amount of energy absorbed at that wavelength. That's how much is done. The calculator, the computer program, is taking care of that. It's calculating that, and that's how it's changing the temperature. So we're up to 1 part per million, and we are still uncomfortable. Not quite 10 degrees Celsius, not quite 50 degrees Fahrenheit. It wouldn't be quite right. Let's go another factor of 10. 10 parts per million from 1 part per million. We go from 49.7 to 53.5. So it did go up, but notice a large part of the spectrum, there's no light at all from the Earth that's being, all of it's been absorbed by the CO2. And only this little wing part on each side is now absorbing, and it'll be widening out as we add more. We're up to 53, that's about 12 degrees, not Celsius. If I go to 100 parts per million, we go from 53.5 to 57 degrees. And again, you notice we're just absorbing more out in this wing on each side as we do that. And this side of the absorption band is pretty steep. Mostly it's just this one that's adding to the temperature now. Most of the CO2 absorption region is saturated, and it's all being absorbed. And we're up to about 14 degrees. I'm going to go in and put in 400 parts per million, which is what we estimate now as the concentration of CO2 in the atmosphere. 400 parts per million. And we're up to the observed temperature of the Earth, 15.1. Is somewhere, the average temperature of the Earth, everybody agrees, is somewhere around 15 degrees Celsius, about 59.1 degrees Fahrenheit. So I can explain the temperature of the Earth from this CO2 black body radiation model, and I get it exactly what's observed. And the nice thing about this model is if you tell me how much CO2 is in the atmosphere in the past, I predict pretty close to what we measure for the temperature in the past. If I put in concentrations above what it is now to see what's going to happen in the future, let's double the concentration. We're at 59.1. Let's go to 800 parts per million. 59.1 goes to 60.2. Doubling the concentration of CO2 in the atmosphere would only change the temperature by less than 1/2 degree if we doubled what we put in there now. Let's put in 1,000,000 parts per million and see where it would level off. Oopsie daisy. In the wrong. I was in the wrong cell. I've got my program protected, so I can't make a silly mistake like that. Okay, if I put in the right number of zeros, that's 1,000,000 parts per million. Okay, 60.2 degrees to 70. Oh boy, now that's a warming. But we don't have to worry about it. 1,000,000 parts per million means that we have a pure carbon dioxide atmosphere. There's no oxygen in it, and we're not here. We're dead too. So until we get into the range of almost a pure atmosphere of CO2, we're going to be in trouble long before we're getting too hot. We're going to be dead because we suffocated ourselves with the carbon dioxide. Now, I don't think that's apt to happen, but I hope you do see that this model works very well, and it's extremely simple, and it predicts the past. These people that use the Cray supercomputers and all of those fancy models that they come up with, you know what? There's not a one of them that can predict the past. Not one of them. If you put into that the concentration of CO2 that was in the atmosphere on the average of that 200 years ago, it will not predict the correct temperature 200 years ago. Now, tell me, why do you think it would predict the temperature 50 years into the future? The models don't work. They get a lot of publicity, but they do what the programmer calls them to do. I didn't write a program to cause it to predict the temperature. What I did was I did the exact calculations I showed you. I calculated the number of parts per million. I took that concentration, predicted how much would absorb at that wavelength. I took that energy and added that back into the atmosphere. If it's an infinite pass, it would work. And then I recalculated the temperature. And this model didn't presuppose that if I put 200 in, I'll get one number. If I put 300 in, I'll get another number, like often the other computer models do. Okay, so now let's go back and see if I can get my PowerPoint back up. Okay.
Are we going to have access to that Excel sheet? Is that going to be on Blackboard if we want to take a look at that?
Well, if you're interested in it, yeah, I can put it up there.
Okay.
Yeah. Now I hope if you use it, you understand how it was how it did, and that the model doesn't presuppose warming because of adding CO2. It calculates how much it should be,
if
and
there's
then
this
predicts
much CO2.
what the temperature would be. Okay.
Right. Okay.
Yeah. Yeah, I can load that file in on D2L for you.
Okay. Thank you.
Yeah, but I wanted people to understand, since we're studying light and interaction and all of this, I thought this was a really good time to talk to you as a trained PhD molecular spectroscopist, how you would actually go about calculating what the temperature should be, and give you a model that does that is based on those calculations. Okay, all right. Enough of that, and no, it's still just 10:30. Let's keep going, because I want to make sure we use our time wisely. Okay, let's go to here. Wait, no, escape out of there. I got to do a screen share first, and I got to go back to here. Okay. Now, I'm thinking the next experiment that I will set up for you is the experiment 10 that's in the lab manual, because I would like to maybe use that to reinforce what we're doing here. And lab and lecture are supposed to correlate with each other anyhow. So I want to look at what happens, and you start looking at the light that's emitted by atoms. Now, if you just take a a, take a piece of tungsten and heat it up till it glows, it gives off a radiation that we talked about as black body radiation. It gives off a continuous stream of colors. Every possible color is there. Our eye interprets that as white light. So if you took this filament and you started heating it up, the first thing you know is it would glow red. If you started heating it up, you could feel the heat coming off of it. That's infrared coming off. If you heat it still further and get it to a higher temperature, then you're starting to emit not only infrared, but some of the other colored light that we can see. The first color you're going to see is it gets red. We call that red hot. And if you heat it still further, the other colors start to show up. And pretty soon you get all three of your sensors picking up light. And it interprets that as white hot. It's giving off all colors. So if you heat up a collection of atoms, a big bulk sample of atoms, that's the kind of radiation you get. If you excite atoms, say pass them through a discharge tube at kind of low pressure, you see that only certain energies of light is emitted as you start heating that sample up. And you see one particular color and another particular color, but nothing between those two, and maybe another color. So you might see different colors of spectra, and we use that in an instrument called atomic absorption, where we can identify substances down to parts per billion, looking at the intensity of the light they emit when we spray them, for example, into a Bunsen burner flame. They will emit colors, but you only see certain colors for certain atoms. The color pattern that you see is a fingerprint. You can tell lithium from sodium and sodium from potassium and all of them from iron. They all have an individualized pattern, and the energy is quantized, which means there's only certain energy levels possible. So while if you think about in our classrooms, you have elevated classrooms, you have little steps in there to go down to the front. But along the side, there is a ramp for people who need to come down who are in wheelchairs. So the ramp type of spacing of energy, potential energy in a gravitational field in this case, that ramp represents what happens to iron or cobalt or nickel or anything that you heat up like that, that's not individual atoms, but just single, but a big collection of atoms. The stair steps is the type of energy pattern you see if you look at one individual atom. Only certain colors are seen in the spectrum, which means there is a lowest state. That's called the ground state of the atom, and everything at room temperature is in its ground electronic state, unless we excite it some way. Maybe we put it in a discharge tube and hit it with an electron beam and produce other energies. These higher states are called excited states. So if you have a room temperature sample not being hit by anything or excited in any way, all of the atoms of that sample would be in their lowest ground electronic state. But if you excite them, they could go to one of these higher states. And you could then, if you got an atom in this excited state, it could fall back to the ground state. When it does that, it gives a certain amount of energy, which has a certain color. I'm showing it as a red line in this spectrum. The electrons that landed, the atoms that landed in this energy state could also fall back to the ground state, and it's a bigger energy gap. So the color of the light goes more toward the blue and violet region. And if you went to the third state, you might get this line, which might be blue. That one looks kind of aqua green. And then you might get this one, which would be violet, or going all the way from this state to this state. So this pattern of colors that you see would identify that particular element. Every other element might have the same pattern, a similar pattern for energies, but they won't all be spaced like this one. And the colors that come off will be unique to that particular substance. Okay, now let's look at hydrogen and measure the wavelengths of the light. This red line is measured to be at 656.5 nanometers. If we put that in our spectrometer, or in the lab experiment, we do that with a little spectroscope. We look down in it and you see this red line. You can measure the wavelength of it, not to that accuracy, but you know it's around 650 nanometers. But if you measure it in a spectrometer, you get 650 times 10 to the negative 9 meters as the wavelength. And we use that equation I showed you earlier to calculate its energy. That comes out to be 3.0279 times 10 to the negative 19th joules. The second wavelength you measure, this sort of aqua color one, is at 486.3 nanometers. And if you calculate 486.3 times 10 to the negative 9 meters for the wavelength, you calculate the energy as 4.0876 times 10 to the negative 19 joules for the energy between this state and this one. The third line is this blue one. It's 435.2 nanometers. Most of us can see that one. So when we do this experiment in the lab, most of us can see that hydrogen line in the spectrum. And it calculates to 4.5781 times 10 to the negative 19 joules. And the next one is this violet one. There's actually two violet ones. The next one up above that, and almost none of us could see that one. This one, some of us could see this one, and some of us could not. Usually say you can see to about 400 nanometers. That's just a rough area. Very few people can actually see 400 nanometer light, and unless it's extremely intense. So this one is hard for a lot of people to see. But most of the time, if you're careful and you've got a really good color acuity, you could see all four of these lines in the spectrum. And we can measure their wavelengths, and we calculate that. Now, these lines you can see are getting closer and closer together. See, the difference between this one and this one is essentially 1 unit, but the difference between this one and this one is 4.6 to 4.8. It's only 0.3 of a unit. So as you get further and further up, they get closer and closer together until they just merge into one line. And that occurs at 364.7 nanometers. None of us could see that, but we could see all those lines instrumentally, and we could get all of those measurements. And that's where these measurements actually come from. Now I want to show you something with these numbers. Now, this is the amount of energy from the ground state all the way to the excited state. Now let's think about physically what that means. A hydrogen is a proton with 1 electron. As I pull the electron away, I reach certain energy states. I pull it out to a certain distance, and I get to this energy state that my cursor is on. I pull it out to another distance, I get to this energy state. And pull it out to another distance, I get this. And the amount of energy it takes to pull them out gets smaller and smaller. The limit, what happens in the limit? Well, you pull the electron completely out and left the hydrogen ion behind. So that means the interaction energy between that proton and that electron at infinite distance is 0. So that's why we've got this limit. And we know how far it is from here from the measurements that we did spectroscopically. It's that much. Now let's think about the binding energy then that the electron would have. If it's completely no interaction between the two, that ought to be 0. So this is where we really ought to set our 0, is up here, not down here at the ground state. We need to know how far that is, that ground state is, from the energy state where that was 0. Well, okay, if I call that 0, the energy from here down to here is this much. It would be energy that would be released if the electron went from infinity and found itself in the ground state of the hydrogen atom. It's released energy, so that energy is lower. It's negative of that. All of our energy, binding energies, are going to be negative. Energy given off when you drop that electron into the atom. It releases the energy, and energy released is always given a negative sign. Okay? Now, suppose I want to know then if the distance from here to here is this much, I know the energy of this line, I can subtract them and find out how far it is from this limit to this first excited state. And we can calculate that. We know that energy is 3.0279 times 10 negative 19. We know that energy is that much. If we add that positive number to that negative number, we come up with this number. So the distance, the energy level for the first excited state of hydrogen from here to here is minus 2.422 times 10 to the negative 19. Now I take the blue line, do the same calculation. There was the energy we got for the blue line. I know the energy of this one. If I add this number to this negative number, I get this value for the binding energy for the third excited state. And then we use the energy of the this blue line to get the energy of the next one. It's that much. I rewrote the numbers so they'd all have this power negative 19. So this would have been 8.7 times 10 to the negative 18. So I put it like that in this format, just to keep all these the same power of 10. Then we go to the next one, and it had that energy level, and we got this energy level for it. And of course, you see they are getting much, much closer together as we go up, just like we thought they should. Okay? And now, let's see what we can do with that. Okay, so here's all of our energy levels. I'll reproduce all of those. Now, let's see if we can see a relationship in some way between these energy levels. And so if I take the 5.45, all of them are negative, all of them have a power of 10, so I just got rid of the sign in the power of 10. And I take the other number, that number, and divide it out. You know what you get? Now, that should start to rock your boat. You saw how we calculate these energy levels in the hydrogen atom. But look how simply they're related to each other. This one and this one divide out to get the same thing you would get exactly to 8 significant figures when we do it correctly. To 9 divided by 4. Wow. So that means that this and this have to equal the same constant. So 4 times 5.4500 has to equal a constant. And 9 times 2.4221 has to equal the same constant, cross multiplied up here. And that means that this energy level, the 5.4500, this ground one, this bottom one, is this constant divided by 4. And the second one is that same constant divided by 9. So instead of doing all this math, I would get the same result if I took some constant and divided by 4 to get this one, and some constant divided by 9 to get this one. Now, let's look at the other conversions. I'm going to compare them all to this one. So I take this next energy level and divide it into 5.4500. And guess what I get? I get the ratio of 16 to 4. This times 4 is equal to this. If we had all the significant figures, it would come out exactly that. So again, the constant is like this. So this next energy level, instead of writing 1.3624 times 10 negative 19 that I calculate, it's going to be some constant divided by 16. Now look at the pattern. 4, 9, 16. You don't have to reply, but can you think in your head what the next number ought to be in the denominator? 4, 9, 16. What's the next number in that sequence? IQ test. Well, let's calculate and see what it is. It's 25. Now, let me ask you again. What's the next number in the sequence? 4, 9, 16, 25. You got it? It's 36. Sure enough. And we didn't calculate the rest of them, but you know what? I can calculate every single one of them, all the way out to infinity with this pattern. Now, I usually tell my students at this point, if this doesn't light your fire, your wood is wet. There's something wrong. If you think about the unimaginable possibility that all the ways that hydrogen atoms could absorb energy and create energy states, it would be this simple. Some constant divided by the square of some integer. It's still, honestly, after 50 years of teaching this, I get goosebumps when I talk about it. It's just so exciting to me and so remarkable to me that the secrets of the universe are just sitting there like gold nuggets for us to trip over. That's about the way this is. It's a nugget to trip over. Now, when I was calling this the ground state, in the general case, that's true. In the hydrogen case, it's not true. This is actually the second energy state. It's the first excited state of hydrogen. Well, you ask, well, where's the ground state? It's about 3 floors down below me. The spacing gets so big between the first and the second level that the light going to the second level, or all the way down to the first level, is not in the visible spectrum. It's in the ultraviolet spectrum that we can't see at all with our eyes. So we don't know it's there. In fact, most of it is, most of that radiation, all of this energy is coming from the sun, but most of it gets absorbed way before it gets down to the surface of the earth with that infrared, in that ultraviolet region of the spectrum for hydrogen. So we can calculate every energy level in the hydrogen atom. And now I can use those to calculate that constant that I know what the energy level is. I know that was 4 squared, so I can calculate the constant. The constant is, from that measurement, is 2.180 times 10 negative 18. I divide that by 9, I get that value. If I do it again for the next one, I get the same value for the constant. And I think they work all of them except maybe one is off a little tiny bit. Yeah, maybe the 36 one. This one is 2.179 instead of taking. So this is essentially 5 independent measurements for that constant. So now not only do we know that the energy levels of hydrogen is some constant divided by n squared, we know what the value of the constant is. it's 2.18 times 10 negative 18 joules. So the energy level of the hydrogen atom is 2.180 times 10 negative 18 divided by n squared, where n is equal to 1, 2, 3, 4, 5, 6. So if I now regenerate my numbers, these are the energy levels of the hydrogen atom. This is the visible spectrum that we see. It lands on 2. All of the lines land on 2. And infrared, we could let them land on 3. This would give you a series of lines in the infrared. Now, this is easy to predict and easy to check. Look, if I take these 2 visible lines and I subtract this one from this one, I'll get that one. If I subtract this one from this one, I'll get that one. So you see, I can take these visible lines and predict the infrared spectrum. And that was done for hydrogen sometimes before those lines were ever discovered in the hydrogen spectrum, in the infrared. They were able to calculate them using this simple model based on just what we observed in the visible part of the spectrum. So, and then the ultraviolet part is this one. And all of these lines are invisible to us. They can be detected by using electronic detection. Our instruments can certainly see in the infrared, even though we can't. We can observe those lines. Now, you would have to be pretty careful. If you did it in a regular soft glass discharge tube like you have in the lab, none of this will come through. And that's pretty good, because we don't want you getting exposed to ultraviolet light when you do a lab experiment. So the glass envelope that the hydrogen discharge tube, all of them, all those glass envelopes are made of a soft glass that absorbs in the everything except visible light. So you're not going to get those other lines in the spectrum in the discharge tubes we have. It won't go out through the glass envelope. But if you made that discharge tube out of quartz, quartz transmits most of that ultraviolet radiation. So you can generate a discharge tube that does show these lines in the spectrum, and sure enough, they are exactly where we predict them to be when we measure it. Now, it turns out the atmosphere absorbs all of this pretty efficiently, except a little bit of this one. This series of lines is called the Lyman series, and this one, the first line, is called Lyman alpha, and has this energy. And we could calculate the wavelength. I don't remember what it was. It's somewhere around 101 nanometers, maybe, something in that range. I don't remember the exact number. But anyhow, it's a radiation that's in the ultraviolet, and our atmosphere does actually let a little of that radiation through. And I've wondered sometimes why, and me and some other scientists think that that's also important to us. Just like CO2 in the atmosphere was important and was necessary for us to have comfortable life on Earth, we needed that greenhouse effect to be in account. And sure enough, it's there in our atmosphere for us that we need it. The Lyman alpha gets through a little bit, and all of these kinds of radiation are called ionizing radiation, and they cause mutations. Now, we got a nasty word for a mutation. It sounds bad and it's awful and we don't want it. And we do have to be a little careful with it. If we get ionizing radiation in us, that's a good chance we'll get cancer. And the ultraviolet light is statistically proven to cause skin cancers. So too much of it is very, very bad for you. But if you get a little bit of ionizing radiation, it can trigger a mutation, which is a change in the gene that it might not be cancerous. it might produce an offspring that has different characteristics and may be more able to cope with its environment. So we believe that this ionizing radiation from Mount Lyman alpha may actually help in the evolution of species. Everything does change to improve itself to better match the environment it's in. That's just a law of nature, and it does happen. You want to talk about evolution? We'll talk about that privately or some other time. But evolution of a species to a better species of the same thing is an absolute documented fact. It does happen. Evolution across from one species to another has never been documented and could have been if it ever happened. And if you study bacterial growth, bacteria proliferate so fast you can have 1 million generations overnight. So if you really wanted to look for evolution of one type of bacteria into a better bacteria or into a virus or something like that, you never ever do see it, although you certainly could if you looked in the test tube, and evolution from one species into another actually happened. Okay. Now, okay, that's good for today. We'll stop right here, and I'll take a couple of minutes, and I'm going to have to close this meeting out and start back up in order for the recording to be processed.